In this video, we're going to talk about how to derive a loss function from utility and vice versa. Recall that in our discussions, theta has always been some unknown parameter or value. We call it the state of nature. And then A is going to be the action that we take. A lot of times it's the estimate of theta if theta is numeric. And then usually, given those two parameters, we can determine our reward, which we call little r. Although we're going to see in a second that there are some times when, even though we know theta and a, that doesn't always guarantee that we can determine at that point what the reward is. But let's first consider the case where it does determine a reward r. And in that case, we know that our utility, which is a function of the reward, can be determined, and we can also denote that as we see here. And then once that has been determined, then we can define loss to be the negative of utility, or vice versa if you're going from loss to utility. In some situations, however, knowing theta and a does not allow us to determine exactly what the reward is. This occurs in the situation where the value theta is a statistical parameter. So there are some situations where once we know what theta is and what our action is, then that leads us to a random variable, or there's still some randomness inherent in the problem, which we model that as a random variable. And then the realization of that random variable is the reward. And in such cases, we define the utility to be the expected value of u of z, which is, again, random, given theta comma a. So let's look at an example of that. Consider the following game. Suppose that we've got some fixed number n, some fixed positive number n, and we're going to flip, a coin is going to be flipped that many times. So, for example, a coin is going to be flipped 10 times. Or it's going to be flipped 15 times. So that's set up front. And then on each flip, if the coin lands on heads, then you win $1,000. Whereas if it lands on tails, you lose $1,000. And this coin, here's the random parameter. This coin has a probability theta of landing on heads. So we're not necessarily assuming this is a fair coin. In order for any reasonable individual to even consider playing this game, I think it's obvious that this unknown parameter theta would have to be 1/2 or greater. So let's assume in this example that theta is 0.6. So we're going to assume right up front that theta is 0.6. Okay, so we know the state of nature here, which again, this is a statistical parameter because it tells us how likely it is for this coin to land on heads. So every time we flip this coin, it's going to have a probability of 0.6 of landing on heads and a probability of 0.4 of landing on tails. And again, if it lands on heads, $1,000 is won, while if it lands on tails, $1,000 is lost. So we have to have some way of representing these coin flips mathematically. And the way we do that is with a random variable. So we're going to let Zi, capital Zi, denote the amount won on the ith flip of the coin. So from this setup, you can see that each Zi is going to be equal to 1,000 with probability 0.6, and it's equal to negative 1,000 with probability 0.4. And the question is, given this setup, and also knowing what n is, do we play the game or not? Would it be beneficial to play the game in terms of utility? And the utility function that we're going to use here is what you see there. And it says this is a utility function for a change. So we're not considering utility in terms of a person's total fortune. We're just looking at the utility in the change in our monetary fortune as a result of playing this game. And so you can see that losses are weighted in a sense twice as bad as a gain. And then for n equals 1, so let's say we only get to play the game one time. So the setup is the coin is flipped one time, and if it lands on heads, you get $1,000. If it lands on tails, you lose $1,000, and that's it. That's the end of the game. So the question is, based on expected utility, would we decide to play the game? And so we have two actions. Either A1, we play the game, or A2, we do not play the game. The expected utility of our random variable Z1, which again, remember that denotes the amount won or lost on the first and only flip of this coin, given our state of nature that theta is 0.6 and that our action is A1, is 0.6 times u of 1,000 plus 0.4 times u of negative 1,000. And remember that the utility function for positive numbers is r to the 1/3, so that'd be 0.6 times 1,000 to the 1/3, or 10, plus 0.4 times, and then for negative numbers, it's 2 times r to the 1/3, so that's going to be 2 times negative 1,000 to the 1/3, that's going to be negative 10. So that's 6 minus 8, which is negative 2. And then if we calculated the expected utility of action A2, then that would clearly be 0, because A2 is if we don't play the game. So if n is equal to 1, if this game is only played one time, then in terms of expected utility, we should not play the game. Now let's look at what happens if n is 2. Remember, n is the predetermined number of times that this game will be played. So here, the coin will be flipped 2 times. One important aspect of this particular setup is that, well, we've got to apply the utility to our total monetary change. And since this utility function is not linear, we can't do like u of z1 plus u of z2. Right? That is not true. So that complicates things a little bit, because if this were a linear utility function, then you can just see that for playing this game n times, then the total utility would be negative 2n, which would tell you, to never play the game. But again, this utility function is not linear. Recall, is what we have here. So we've got to calculate the expected value, given our state of nature, and we're just considering the action where we play the game, because if we don't play the game, the expected utility is 0. So how do we get that expected value? Well, we've got to know the distribution of this sum, and these are independent random variables, right? Each time we flip the coin, those are independent events. So we need to determine the distribution of the sum of two of these independent random variables that are identically distributed, right? They're each time the coin has a probability of 0.6 that it lands on heads and you win $1,000, and lands on tails with probability 0.4, and then in that case you lose $1,000. So we've got to think about all of the different possibilities that we could get here. So we could have Z1 be 1,000, land on heads and be 1,000. Or Z1 could end up being that we lose 1,000. And then Z2 similarly, the second toss of the coin, it could land on heads, and for that second play, you would win $1,000. Or for the second play, you could lose $1,000. So we've got to think about the associated probabilities with each one of these possibilities. So we've got to come up with a joint distribution of these two random variables. Well, remember that these are independent random variables. So if we win both times, that's going to occur with probability 0.6 squared, which is 0.36. The probability that we win the first flip and lose on the second flip, that would be 0.6 times 0.4, which is 0.24. Similarly, if we the probability of losing on the first flip and winning on the second flip, and then the probability of losing on both flips would be 0.4 squared, which is 0.16. So then the distribution of Z1 plus Z2 is, well, it's 0.36 it's equal to 2,000 with probability 0.36. And in the situations where you lose one time and win one time, that sum turns out to be 0, and that would be with probability 0.48. Because remember, there are two different situations where that can happen. And then if we lose both times, that would be negative 2,000, and that occurs with probability 0.16. So with probability 0.36, we would win $2,000. And then with probability, we would have one win and one loss, so we would win nothing. And then with probability 0.16, we would lose $2,000. So then that's 0.36 times 2,000 to the 1/3 plus 0.16 times, and then remember for negative numbers it's different. It's 2 times r to the 1/3. So it would be 2 and then times negative 2,000 to the 1/3, which would be 0.5039 and some change. And then of course the expected utility, if we choose action A2, which is not to play, that's going to be 0. So in this case, it would be feasible to play the game. One important takeaway from this example is that whenever the reward is determined in a random way, we can't just look at the utility of the reward. We define the utility for that state of nature and that action to be the expected value of this random utility, if you will, given theta and little a. So in the above examples, we were actually calculating u of 0.6 comma a1, and then u of 0.6 comma a2 always was 0.